Thank you very much for the introduction. I would like to thank the organizer for their invitation, in particular Bodino-san and Sasamoto-san. I'm really very much honored to be at the IHES. So I'm going to tell you about some works we did during the last 5-6 years with Imamura-san, Sasamoto-san, and students and collaborators. And we are interested in the symmetric exclusion process. So we are working on interacting particle systems, and I'm a physicist. So the interest comes from non-equilibrium statistical physics, trying to see how systems respond to an external drive, and what are the fluctuations out of equilibrium in a system like the symmetric exclusion process, which is a kind of Ising model for non-equilibrium physics. It's really the model that people try to understand and try their hands on before going to more realistic systems. So I don't want to do a long physical introduction. I will just pose a problem. You're mathematicians, you like well-defined problems and well-defined systems, so no bullshit. I take the symmetric exclusion process, particle hopping on a lattice with exclusion interactions. It's a continuous time system, and I cannot put two particles at the same place at the same moment. So some moves are allowed, some moves are unallowed, forbidden. And my initial condition on Z is that I put Bernoulli independent, I put densities on my lattice, and with two different densities on the negative side, rho plus and rho minus on the positive side. Typically I put more particles on the left and less on the right, and I look at my system who's flowing, and I count how many particles have jumped through the 0-1 bound. So I count, and this is a counter, which is, of course, I count positively from left to right and negatively from right to left. And Qt is a random variable. It's a total integrated current in my system. Really imagine a fluid which is flowing through my one-dimensional pipe. And this random variable, I want to characterize it. I want to compute its large deviations, its cumulant generating function, and maybe even its full distribution at finite time. We shall be able to achieve that. So, I'm again another problem which is very closely related to the previous one. I do the same system, but now I tag a particle. I tag a particle that I put at position 0 at time 0, and again I have my two densities, more on the left and less on the right, or the opposite. And I monitor the position of this blue particle, same dynamics as the others, but I'm just looking at it, and I call xt its position at time t, and I want to know the statistics of xt in the long time limit, or maybe even for all times, given the boundary condition, the initial conditions. By the way, because the exclusion process, there is no crossing of particles in 1D. In fact, the statistics of xt and the statistics of the current through a bound are very closely related. Just by using this non-crossing condition, we are going to see that in more details. So this model has been studied a lot for many, many years. I think it was introduced by Spitzer in the mathematical literature in the early 70s. But people in biophysics also studied it for some RNA transcription reasons and so on. Because it's a minimal model, it popped out in many, many different systems. Physical chemistry, soft condensed matter, mathematics, of course. So because of symmetry, of course, the average of the position of my tracer is 0. If my particle were not interacting at all, I would have just a bunch of random walkers. So my diffusion would be normal, x squared would be dt. But in fact, because of this exclusion condition, Arnatia showed 40 years ago that x squared grows like square root of t. So that's an example of anomalous diffusion, diffusion in t to the power 1/4, maybe one of the simplest way to realize it. Much more recently, well, 10 years ago already, Seturaman and Varadhan showed that the large deviation principle is satisfied by this random variable xt, but you have to rescale things with square root of t instead of t. But this is very nice for mathematicians, but maybe not so much for physicists. It's nice to know that LDP is satisfied, but as physicists, we would like to compute the rate function, not only to have bounds, not only to know that it exists, we would be ready to compute it even if it did not exist. So, you know, that's the difference between math and physics. One of the differences. Anyway, and even better, could we compute the finite time distribution of this position variable? So the answer is yes, of course, otherwise I won't be here. But one way, so I'm not going to give you details. Of course, it's impossible. I will just try to stretch on some strategies and give you some keywords, hoping that these keywords will talk to some of you or raise your interest. So one usual way is to go from a particle system to an interface system. This is the usual, slight variation here, but the usual KPZ and AZEP or ZEP mapping. Essentially, so it's a slight variation. Usually you have up and downs. Here, when the site is empty, my interface is flat, and when the site is occupied, I go up by 45 degrees. So this configuration is represented by this blue slanted curve. And of course, I have to fix the overall height of this curve, because for the moment being, I'm just fixing the slopes. So the overall height of the curve above site 0 is given precisely by my current, my total current that has gone through the 0 bound, 0, 1 bound, counted, of course, with algebraic signs. So now I know exactly the interface. And I can see that through this definition, essentially, I have defined a height everywhere over any site. And the height everywhere is the height at 0 plus the number of ones of occupied sites I have between 0 and site x. Okay. So that's another way of defining an interface. The usual one is just slanted by x over 2, and you would go back to KPC. So now, these things are simple, but always very difficult to explain, so I'm not going to try it. But it's in fact very simple, because particles cannot overtake each other, so you could, by taking time, even explain it to a kid. So you have to convince yourself, and maybe I got my signs wrong, because I was doing that very late last night. So, but I think the probability that your tracer have moved further than x is the same thing as the probability that the current or the height nxt that I've just defined at point x is positive. Okay, it could very well be negative if I made a mistake, but there's a simple relation like that. Just because to move further than a certain point, you have to push the guys which are in front of you between your position and the position x. Okay. So finally, again, the statistical properties of my tracer's position are encoded in this bunch of variables nxt. And this is very nice because x of t, the position is moving, so it's a kind of, Lagrangian variable. And we are in fact now trading the knowledge of xt to the knowledge of the height over a given site, and that's much easier because it's a fixed variable. But of course, there is no free lunch. Now we have to deal with a numerable bunch of, you have a whole set of nxt's for all values of the position small x. But it's enough to focus on these guys. So first of all, I will tell you in this talk, if I have enough time, about two approaches on the same problem. The microscopic approach, which relies on techniques of integrable probabilities, Bethe-Ansatz, Tracy-Widom formula. And second, which is more to interest to us nowadays, to Moiro, myself, and our students and collaborators, a macroscopic approach. So let's start with the microscopic approach, and we're happy also to work with Takashi Imamura, who gave a talk yesterday. And I just give you the result, just to focus on it. The characteristic function of exponential lambda of this height nxt at point x at time t, at any finite value of x and any finite value of time, there is no asymptotics here, is given essentially by a freedom determinant times some multiplicative function. So that's an exact result, and I think it's even mathematically kosher. So it's published in CMP, and there are proofs. And here there are a bunch of, parameters. One important parameter is this omega function that appeared everywhere in these studies, in all papers by Thierry and Bernard Derrida, and other papers, even maybe by Bernard even before. So this omega factor contains the densities on the left and on the right, and this fugacity, this Laplace parameter lambda, in the form exponential lambda plus or minus 1, and so on. The kernel here in your freedom determinant is perfectly well defined, and it is related to something which in physics we call Bethe-Ansatz, of the Tracy-Widom formula. So it's a kind of rational function multiplied by an evolution operator. And this prefactor here is not so important. It's a kind of Poisson type of formula which encodes the far boundary conditions. But again, I emphasize that this is an exact result and not at all an asymptotic result. Asymptotic will come later from the freedom determinant. So the strategy is the following, and this I'm going to go fast. First of all, we have to go from ZEP to AZEP. So the same problem can be stated in AZEP. AZEP is just the asymmetric version of the exclusion process. Now you can jump to the left or to the right with different probabilities. So you put an external field which pushes your particles, that's in the right direction. Okay? AZEP is characterized by these two parameters of jumps, but of course the only relevant parameter up to rescaling of time is just the ratio of forward rate by backward rate. And this ratio that we call tau can be chosen less than 1 just by exchanging, we favor jumps to the left, let's say. Okay, so now the strategy to solve this problem is to turn into the asymmetric exclusion process. The difficulty of this problem is that if you try naively to compute this kind of object, you will find that the evolution equation for this characteristic function is not closed. You will need to have correlators between, heights at 2 points and height at 3 points and so on. As usual, we call this in physics the BBGKY hierarchy of correlators, which goes up and up. So you have to break the hierarchy, otherwise you will never be able to solve the problem. And you can break this hierarchy, fortunately, by using a property which is called duality, which was very much studied by, again, Takahashi and Tomohiro and Christian Giardina and many other people. And this is the miracle that instead of considering correlators of n, which would be the natural thing to consider, it's much better to consider correlators of tau to the power n, where tau is the asymmetry factor in AZEP. And then, by miracle, you can prove it either by algebra or by just using Poisson calculus. In fact, these correlators, tau deformed or tau exponential correlators, they are closed. They satisfy closed, for example, a n correlator of this type satisfies a finite, among themselves, the evolution equations are closed. So then you're happy because you're back to a finite problem. Finite n. So you can solve this problem by using Bethe-Ansatz and the so-called Schutz-Tracy-Widom type of formulas. So again, this would require a long time to explain, but you can find an exact solution for these evolution equations, for these correlators, which now are closed. So their evolution equations just involve themselves. You can solve them by using some contour integrals in the complex plane. So that's the machinery of Bethe-Ansatz, an integrable probability. And again, this is an exact solution. So that's an exact representation for these tau correlators. And once you have them, so this is for AZEP, you have to go to the symmetric limit, and you have to, there's a major difficulty here, you have to do very complicated, contour integrals with some untangled circles. And one major step in the problem is to do residue calculus for multiple complex integrals, which means to disentangle these circles. And when you do that, you have some combinatorics coming in, because you have to compute residues, and residues which are inside the contour, and then you have to open the contour. And because there is many of them, as we say in French, a mousse, so it becomes a big mousse. But anyway, you can track the contour residue calculation, you can track the combinatorics and obtain, again, combinatorial formulas where many of these integrals are disentangled. I'm going too fast. Much too fast. Pourquoi, qu'est-ce que ça fait là? Comment je fais pour remonter le temps? Well, ça y est. I can't go back in time because it's precisely, it's irreversible. Non-equilibrium statistical physics is irreversible. Anyway, so we can do that. And then we can take the symmetric limit, tau going to 1. We had to go to the asymmetric case because duality, as we need it, only works in the asymmetric case. We don't know how to make it work. There is a kind of duality in the symmetric case, but we don't know how to use it for the problem we are interested in. So in the end, by reordering this combinatorial formula, we can recognize, using some identities for determinants and so on, you can recognize this determinant that I told you about. And then the next step is to do asymptotic analysis of this determinant. And you find that in the long time limit now, long time limit, and scaling limit for x, which has to be rescaled at square root of t, square root of 4t, you can find that this characteristic function behaves like exponential minus square root of t, some mu psi of lambda, which is a cumulant generating function, and we get a closed formula for this mu. So I'm just asking you to try to remember by heart this formula, because it will come back at the end of the seminar. So that's one way to get the formula. It's not a horrible formula. It contains R functions, essentially, some polylog 3/2, and some nice factor, which is again Poissonian type. Okay, so we are happy with that, but not so much as physicists, because this is hardcore technology. And somehow the problem that we asked at the beginning is a kind of elementary problem, just computing the fluctuations of the current. And we would like to have a more physical picture on a coarse grain level, not trying to disentangle the combinatorics at the microscopic level, but have a kind of physical hydrodynamic derivation of, if not the determinantal formula, but at least the coarse grain. You see here, we are doing a diffusive scaling for space, a long time limit. So we are really on the, coarse grain range, and we would like to extract that directly. So that's what we managed to do in a completely different way by using the so-called macroscopic fluctuation theory. So that's again another story. But in some sense, that combines hydrodynamic limits, fluctuations, and physical point of view. If we consider that I have a bar of metal between two reservoirs at different densities of temperatures, it would be, at least again for physicists, quite natural to write a continuity equation. And this continuity equation tells me that because density is conserved in the bulk, the time derivative of density is minus the divergence of a current, and the current has two origins, a gradient factor, that's very natural, Fick, Fourier, whatever you like, and some factor which comes from the fact that I have some asymmetry, some external field, so I have to multiply the field by the conductivity. So the current is just given by gradient rho plus sigma rho, or sigma, which is the conductivity. So that's on the average level, but we want to take into account fluctuations. We are not only interested in on the mean current, but also the fact that the current fluctuates. So that's the goal of a kind of, so that's not rigorous anymore in general. I will give you one case where it's rigorous. But in general, we could say that when we connect two reservoirs at different potentials or temperatures or densities, I do have a mean flow of current between them. I do have a mean density profile or temperature profile between them. This is, let's say, low temperature, so the current should go in the other direction, sorry for that, and high temperature. But I can have fluctuations. I can have my local current that fluctuates from place to place and time to time. And I can also have a profile which could fluctuate around the linear, typical profile, average profile. So you can imagine that there could be a kind of functional large deviation principle for the local current in space and time, for all x between 0 and L, and all times between initial time and final time, and for the local density rho xt. So of course this is not a rigorous writing at all, but you could imagine that there's a kind of rate functional which depends on j and rho, and if we're able to compute this rate functional, we would have a hand on non-equilibrium fluctuations of transport in one dimension between two reservoirs. And then by contraction, we could get information on the current alone or on the density profile alone, and so on. So there is a kind of looking for a principle that would determine this rate function for driven diffusive systems out of equilibrium. And So I rewrote this rate function as an action function. And somehow 20 years ago, the group of Rome, including Claudio Landim, which is still considered as a Roman in physics literature, although he's not, around the fatherly figure, the driving figure of Jona-Lasinio, proposed a kind of very general theory. Again, not a mathematical theory, but a kind of ansatz, physical ansatz, saying that this large deviation functional for the current and the density should take a variational form, which is in fact quite natural, which essentially tells you that locally the fluctuations of the current are Gaussian, like Gaussian white noise. So this would be a kind of very natural variational form to write. But for now, I will take this as a kind of, black box, take it as being true, and try to work on this variational problem. So consider that this is the correct expression for the fluctuations and the large deviations of any driven diffusive system under some hypothesis that I don't really master, but ZEP falls into that. And now if you look in the long time limit and large space limit of this problem, it's again quite natural to imagine, so this is a kind of path integral, that only the optimal path, the ones that optimize this action, that minimize this action, will contribute to my phenomenon, to my measure. So what we have to do is just to now, we are back to a kind of very mechanical problem. We have a variational Lagrangian, or S, an action, and we want to compute its optimal path under constraints, boundary and time constraints. So we want to optimize this action under constraints. So that's Jona-Lasinio. And one of his driving ideas was to find a nonlinear generalization, this MFT, of the linear response fluctuation theory of Onsager and Mallick, which dated from 53. So of course, once you have a variational principle problem, you can write Euler-Lagrange equations, but they are highly nonlinear and complicated to solve, and that's precisely what I'm going to talk about now. So Euler-Lagrange equations, but because it comes from a variational principle, a kind of mechanical principle, you can do Legendre transform and turn it into Hamilton's equations. So I'm going to give you the Hamilton's equations. So maybe I will pass the physicist derivation of this kind of principle, the physicist explanation. But one very important point that I want to emphasize, that although the general theory is still not on very firm mathematical ground, for the case of ZEP, the large deviation principle was established by Kibnis-Olavaradan a long time ago. So you can say that the ZEP version of the MFT, the ZEP case of the macroscopic fluctuation theory, is indeed on firm grounds. So it's good to start with that. So the equations that we are looking at in their Lagrange form are like that. So you remember the Euler, in the Hamiltonian form. The Euler-Lagrange equation, if I had written them by doing variational calculus, I would have obtained equations for rho and j. Now I turn to Hamilton form by introducing a conjugate variable for the current h, and I get this very nice set of coupled PDEs, deterministic, because I'm looking only at the saddle point of my action. And this is a Hamiltonian system, because I have an underlying Hamiltonian h, tilde, h Gothic, and I can derive this equation just from this Hamiltonian h. So that's a kind of very general system, which supposedly encompasses any diffusive non-equilibrium system. And this is a macroscopic system already. I'm not talking about, microscopic structure anymore. But the only information for microscopics comes from this diffusion coefficient, d, and the conductivity sigma. And for this diffusion coefficient and sigma, I have no choice but to extract them from microscopic level. Just as in Euler equation, Navier-Stokes equation, you put the viscosity and things like that by hand. You cannot compute them from first principles macroscopically. You have to really, if you compute them, it's from microscopic physics. So here microscopic physics is entirely encoded in the formulas for d and sigma. And in the case of ZEP, as I showed rapidly, D is extremely simple, just 1. And sigma is 2 rho, 1 minus rho. How much time do I have left? Just completely lost with time.
23 minutes. Exactly.
20 minutes? 20.
20.
Okay, it's perfect. So just halfway. Halfway. Good. So, so these are the equations, the macroscopic equations we are interested to solve, and we want to apply it again to our problem of, height and xt over any site, and in particular, let's say, the current through 0. So if you remember, I'll go back fast, now that I know how to use this thing. If you remember, the microscopic definition of height was current at 0 plus number of particles between 0 and x, okay, so because of my interface. So this is very easy to translate into macroscopic continuous variables, and just a little thinking allows you to write that at macroscopic level, the height, so now I use capital variables for macroscopic. Yes, the height over x at time t is just given by the integral of the density at time t minus the integral of the density initially minus this term. So that's the current passing through 0, and that's the number of particles between 0 and x. So it's exactly the same thing, is a continuous limit of the previous formula. And again, we are interested in computing the characteristic function at the macroscopic level of this height over x and t. So the question is, if I want to compute, for example, the large deviations of this variable, or even the characteristic function with a given value of the Lagrange multiplier lambda, or the fugacity lambda, we could ask ourselves, what is the typical profile and the momentum field, or the current, which generate a given unlikely fluctuation of your local height. And I emphasize again, we computed this object microscopically by Bethe-Ansatz, but we don't want to talk about microscopic physics anymore. We really want to get this function macroscopically using the fluctuation hydrodynamic and the macroscopic fluctuation theory proposed by Jona-Lasinio et al. So what we have to do, at least the program is simple, a priori, we have to take this measure for all possible realization of the current and the density profile, and we have to average over this measure the quantity we are interested in, which is exponential lambda n. Okay? So we have to compute a path integral. But this path integral will be dominated by saddle points of the action, and we want to compute saddle points. So long story short, what we have to compute in the case of ZEP, to compute the height fluctuations, we have to solve these coupled equations, which are the MFT equations, and after some work, you can realize that you have non-local boundary conditions. You have one boundary conditions at the final time, which essentially tells you that you have computed the total current which has flown, or the total height, sorry, that had flown at position capital X, and some initial condition, which also contains the initial profile. Rho bar is the initial profile, rho minus on the left, and rho plus on the right. Okay. So now the mathematical problem, in some sense, is well posed. You have a set of PDEs, nonlinear and coupled, with boundary conditions, and you want to solve them. And once you have solved them, so let's call the solutions rho star and h star, once you have solved them, you can compute the cumulant generating function just by plugging the optimal solutions into the formula that I wrote for nxt. So the program is simple. The question is, how do you solve these equations? And now comes the difficulty and then the miracle. So these equations are supposed to be purely macroscopic. They're supposed to solve your question, solve your problem. But these equations are mathematically difficult. You can even see that there is a a negative sign here in front of the Laplacian, so it's dangerous to say the least. Very few time-dependent solutions were known for these equations, mostly in theory again with Bernard Derrida explored many cases of stationary solutions or the stability of stationary solutions, seeing that something non-stationary happens at some point, signaling the existence of a dynamical phase transition. But I think there was no closed solution for dynamical equations in the case of MFT. But a couple of years ago, in similar problems, there were a few progress by Kragenbrink, Ledussal, Bettelheim, Smith, and Mearson, and the group of Olivier Bénichou, Grabsch, Poncet, Riscala, and Illien, and by ourselves, that allowed to crack down these equations, which has remained written but unsolved for quite a few years, almost 15 years. So I'm going now to explain to you how we did that. So we did that by using the beautiful technique of inverse scattering, which was developed for solitons in the 70s by people by Lax, Newell, Ablowitz, Segur, and many others. And we applied that to MFT in a series of papers. So this one is already published. This one is just put on the archive. And this one, we hope to finish it soon. We have been hoping for a long time to finish it soon. But yeah, we hope so. So maybe the simplest case that I want to tell you about. We have been talking about random walkers and with exclusion, the exclusion process. Let's go to a kind of large distance limit, low density limit, and do a kind of physical approximation, which can be shown to be exact in some limits. We replace our random walkers by Brownian motions. And these Brownian motions reflect against each other. So now we have a bunch on the continuous line of reflecting Brownian motions. And when two Brownian motions meet, we just exchange the labels and they reflect à la Descartes against each other. So in that case, the MFT equations are still valid, but they become much simpler. In fact, the sigma becomes equal to rho, or 2 rho, to 2 rho. And the equations become like that, and the boundary conditions are the same as before. And these equations, although they look a bit complicated, but this one you see is closed in H, they can be disentangled, they can be decoupled by using the so-called Hopf-Kohl or Kohl-Hopf transformation. So by going essentially to V is equal to exponential of something, H, and U is equal to rho exponential minus H, if you plug U and V into this system, you get two decoupled heat and anti-time heat equation for U and V. So somehow you free the problem, it becomes diffusive, non-interacting, and you can solve everything. So you can at least play with this case and compute large deviation function of the current of a tracer position. Calculations are a bit, not hard, but demanding, but it can be done. Okay, now I'm going just to tell you the answer by Serempenditi. Always trying to use this word, not so easy to say. Working on the problem for the symmetric exclusion process, which is here, we, in fact, essentially our young, talented student, Moria Kuhn, found a transformation that generalizes the Kohl-Hopf transform mapping. And when you apply this transformation to the MFT equations, you end up with this nice system for the two variables U and V to the unknown functions. And this nice system is very symmetric in U and V. It is still coupled, of course, you don't decouple them. And this system is known as the EKNS system, Ablowitz, Knaup, Newell, Segur system. And these equations are in fact a real form of the nonlinear Schrödinger or Gross-Pitayevsky equation. And these equations are known to be exactly solvable. They are known to be integrable. So the miracle is that through this transformation, you transform the MFT problem for ZEP into a system of solvable equations. And these solvable equations, they have been very well studied, but the boundary conditions that we have here, which are non-local, are a bit new for these equations. So we have to adapt the procedure that was developed, this inverse scattering procedure that was developed to solve them to this new context. But anyway, we end up with classical equations. The whole mystery is into this transformation, which looks barbare if you look at that like that. But in fact, there is an explanation for this transformation that I'm not going to give here. But we are exploring and going deeper in our understanding of why this works. Anyway, this works. This works, and the second miracle, which is in fact maybe the greatest miracle, is that the boundary conditions, which looked quite awful in terms of the initial rho and h variable, they become just delta functions. Okay, it's non-local. You define the function u at initial time, the function v at final time, but just with delta functions. So this AKNS system, which is a kind of generalization, if you want, of the Korteweg-de Vries equation, and it's close cousin to NLS, it is a Hamiltonian system with an infinite number of conserved quantities. It has a so-called Lax pair, so it can be rewritten as a kind of compatibility condition between two linear equations, and the whole machinery of soliton exact solution of infinite dimensional Hamiltonian systems can be applied to it. So I'm going to rush through it very fast, but the idea is that you can define two matrices, U and V, with some parameter k, which is called the spectral parameter, and which contains the unknown functions U and V here, and here, and here. And you can write, for a vector which is psi, which is 2 by 2, you can write two equations, one in space and one in time. And these are linear equations governed by the matrices U and V. But of course, ddt of the first equation must give ddx of the second one to have compatibility, to have Schwarz compatibility. And when you do this compatibility condition, you get this identity, which is called the zero curvature condition on these matrices, because there's a geometric interpretation for all these things. So it's a kind of curvature condition, or Kirchhoff integrability condition. And this zero curvature condition, if you spell it out, you know, you do ddt of this, ddx of this, you compute the Lie bracket of this, you spell it out, you will find that this compatibility condition is exactly equivalent to the AKNS system here. So this is the so-called U and V form the so-called Lax pair for your AKNS equation system. And once you have the Lax pair, you have in fact a scattering process. This is a linear problem, okay, with unknown potentials, but you can play, you know, scattering and inverse scattering. So I think I'm not going to enter into the details of the scattering process, but the idea of scattering is that you can reconstruct the potential by sending plane waves into your problem. And if you know how plane waves are scattered through your potential, so you have some scattering coefficients, A, B, A bar, and B bar, which represent how a plane wave arriving from the left is scattered to the right. So typically, if you remember your basic optics lectures when you were children, you have a transmission coefficient and a reflection coefficient. So if you know the transmission coefficient and the reflection coefficient for all wavelengths, you are essentially able to reconstruct by holography the index or the form of your glass object, of your transmitting object. Okay. So that's the idea here. By sending plane waves through this scattering problem with unknown coefficients U and V, you may be able to reconstruct U and V from the knowledge of A, B, A bar, and B bar. But for the moment being, of course, you can tell me I know nothing about A bar, A and B, and A bar and B bar, which are just defined as being the scattering amplitudes. Well, the miracle comes because for the moment being, I only use my first equation in my Lax pair. The miracle comes that because of this compatibility condition that I told you about, if I know the scattering amplitude at a given time of the first equation, the second equation tells me how these scattering amplitudes evolve with time, and their evolution is extremely simple. The A and the A bar do not vary, and the B and the B bar just diffuse. So I know that if you have never seen that, this looks complete, I would say Japanese to me, but for you it's okay. So to half of you, so maybe Hindi to most of you. The thing is, this AA bar and BB bar, this is a Hamiltonian system with conserved quantities. Doing this transformation is the same thing as in classical mechanics, going to action and angle variables. That's one way. Another way of understanding it is that what we are doing here, and this is a precise analogy, is a nonlinear Fourier transform. If we had to solve the heat equation, we would go to Fourier transform, and A would be the amplitudes of the Fourier mode, which are conserved, and in fact, this exponential by k squared t would be just the evolution of the mode, just by diffusion. Okay, so inverse scattering is nothing but, I mean, it's much more, but it's a kind of nonlinear generalization of Fourier transform, but it doesn't work for all nonlinear equations. It works only for integrable linear equations, which essentially have this kind of thing, which is called a Lax pair. So if you have that, and the big luck that we had is that we understood that the MFT equations for ZEP enter into this field. They can be solved by this machinery. And now, if you know these, scattering amplitudes at any time, by inverse scattering, knowing the diffusion, the transmission and the reflection rate, you can reconstruct the potentials. So that's essentially what we did. There's some little other trick that I can't really go into, but what we did is that we did direct scattering at initial time and final time. This gave us some information about the scattering amplitudes at initial time, some information about the scattering amplitudes at final time, and then by using time evolution, which is trivial for the scattering amplitudes, we could find some closed equations for these scattering amplitudes for all of them, and then solve them, and then by inverse scattering reconstruct the potential, the U and V. So, okay, so these are just calculations and so on. Again, I don't want to bother you more, but the final thing was, and I think it's more explicit here, so that's my profile at final time. That's the Fourier transform of my profile at final time. And everything in the end boils down to a Riemann-Hilbert factorization problem for my Fourier transform of my profile. So if I'm able to solve this Riemann-Hilbert factorization problem, so this is the positive part of the Fourier transform, which is analytic in the upper complex plane. This is the negative part of my Fourier transform, which is analytic in the lower complex plane, or maybe the opposite. And the product of these two things have to be equal to a given function, which is essentially a Gaussian. So this kind of Riemann-Hilbert factorization problem in one dimension are easy to solve. You essentially have to use Cauchy formula. And you get the expression of the Fourier transform of your profile. And once you know your optimal profile, you just plug it back into the action and you compute the cumulant generating function. And as you learned it by heart 10-20 minutes ago, you can recognize that this is exactly the same formula that we got for microscopic calculation using the better ansatz. So, and of course we can do more. At macroscopic level, we can compute the profiles, which we are not able to compute using better ansatz at the microscopic level. But at least one lesson is that if you think about it, we started with a very well-defined problem, which is a kind of combinatorial problem, with particles hopping on a lattice, and we were counting, we had a kind of discrete counter here, and we wanted to compute the statistics of this variable, or anywhere, any height anywhere. And we were able to solve it by using a very, precise, discrete, microscopic, combinatorial analysis. And the same result arises by solving, the MFT equations, which is just a set of coupled PDEs with boundary conditions, and the same result is embedded in both levels. So you can say, I'm trying to talk like a mathematician, that is a kind of commutative diagram here. Either you solve things exactly microscopically, and you take a large scale, in space and time limit, and you derive your mu. This is the better-on-that point of view. Okay, and you get the mu. That's the first part of the talk. Or you go immediately from your problem to a fluctuating hydrodynamic coarse-grained level. You write some kind of equation, which is a hydrodynamic equation plus noise. You analyze this equation by doing path integrals, saddle point analysis, writing PDEs. For a physicist, it's much more natural to play with PDEs than to play with better-on-that, usually. I mean, PDEs is a familiar object. And if you're able to solve these PDEs, so you're already at the macroscopic level from the very beginning, you get the same large deviation function or cumulant generating function. So first of all, this was nice because this macroscopic fluctuation theory is still on unfirm level. So any derivation using it, adding the noise, I mean, hydrodynamic limits is of course very, very firm, but adding noise is always a bit shaky. Noise is shaky. And if you're able to do the calculations at two levels and match them, this is very nice. Besides that, macroscopic fluctuation theory is more versatile. As I told you, microscopic physics is only encoded in sigma and d. And if somebody tells me the values of sigma and d, I can always put the equations in the computer and get some profiles and get some values, try to do some asymptotic. Once I have PDEs, I can try to do, WKB. I can try to do many things with PDEs. It's very, there's a huge bunch of knowledge which has been developed for that. So now, we are, again, trying to compute other quantities, but we are quite happy that we have been able to compute the optimal profiles. So this is an information also, and each time I say the same thing, but I should really try to do a movie. You can see how unlikely fluctuation is generated in your, it's almost finished, in your system. It's generated by, if you want your tracer to go very far, you have to take a fluctuation where you have more particles in front of it than behind it than in front of it, and this kind of wave will push your tracer away into your system. So it's time to conclude. I hope that I convinced you that the exclusion process is also interesting for physicists. It's interesting to study it microscopically, macroscopically, and the fact that there's a relation between these kind of diffusive systems that we are studying and the inverse scattering method, which was invented in the 70s to study nonlinear dispersive hydrodynamics, is again also a kind of puzzle that we want to understand better in the future. Thanks for your attention.
We have time for one or two questions.
Thank you for this nice talk. Are there some other examples of sigma and d where you can apply the same technique and using inverse scattering?
Yes. So there is. Of course, this is here. It's here. It's even in the conclusion. There is another example which is called the KMP, Kipnis-Mercuro-Presutti model, which is a model for heat transport in which you don't have particles, but you have a continuous variable over each side, which represents an energy, and you redistribute it. Okay. So in this case, sigma and d are known. They are different, but not so different. D is equal to 1, and sigma is 2 rho square. But the fact that sigma now is, convex, and before it was concave, changes a lot of physics. And in that case, a group in Jerusalem, Bettelheim, Smith, and Mearson, were able to solve the MFT equations. Another example is the example studied by Kragenbrink and Le Dussal, which is not exactly MFT. It's KPZ under weak noise. So they wanted to find the optimal realization of KPZ under weak noise and compute the statistics of the height for this case. And again, they used inverse scattering. And we are looking for more examples. We are trying to explore. In fact, first of all, there are mappings between models which look very different, but nonlinear transformations. For example, there's a case where D is 1 over rho, so it looks very different, and sigma is I don't remember what. And you can, this is the so-called Hammersley process or something like that you can map to ZEP. And yeah, so under exploration.
One more question. So you have the profile at the beginning and at the end, but a priori with your A, you say you know everything. So now I'm puzzled. How come you can't get the profile at intermediate time?
Because you're right. I mean, because we have to perform inverse scattering. Inverse scattering amounts to solving a set of linear integral equations, which are called the GLM, Gelfand, Leviton, Marchenko equations. And then you have to do the, so numerically it will be easier now because it's a linear problem, but getting explicit formulas, we don't know yet. We are hoping with Tomohiro that maybe there's some determinant, Fredon determinant at intermediate time. Le Dussal alludes to that in one of his papers, but we have not seen explicit expressions yet.
Okay. So, thank you very much again for this very